some year they have given problem, sometimes they have not. So we can't say. But very, very important chapter. Okay. I told you already about the magnetism and all. Here we are going to study what happens when a charges move in the magnetic field. So moving charges and magnetism. Already you started with current electricity. We have seen when a current flows through a conductor, it produces different effect. One is chemical effect, another is electrical effect, another is heating effect. Like that, one more effect is called magnetic effect. So in this chapter, we are going to study about the magnetic field created by a conductor carrying current. So whenever a conductor carries current, it creates its own magnetic field. So obviously we are going to study if it is creating a magnetic field, how do I calculate that? Fine. And not only that, what is the application part? Whenever scientists discover something, always they will see what is the application part of it. That is what we are going to study here. So remember one thing, when a current flows through a conductor, a magnetic field is set up in the region surrounding the conductor. Means around the conductor, you will see a magnetic field. And remember, a magnetic field is a vector quantity. Therefore, whenever I am studying this particular chapter, remember the direction is very, very important here. Okay, this entire chapter depends on what is the direction of magnetic field, what is the direction of current. If I've understood that, then this chapter will become easy. Clear? Okay. So before we go this one, let us check what is the brief history of this. So before 18th century, okay, before 18th century, scientists were not aware that electric field and magnetic field. Before 18th century, scientists were not aware that electric field and magnetic field are interrelated. Okay, and they used to study them separately. In the sense, there was no connection between the electric field and magnetic field. Electric field was studied separately. The way electric field is studied separately, magnetic field is also studied separately. For example, whenever you defined electric field, you said it is the space around a charge where another charge experiences a force. Similarly, before 18th century, they used to define magnetic field in the same way. Magnetic field is the space around a magnet where another magnet experiences a force. Remember, now this definition doesn't hold good because that was the definition what they used to use before 18th century. Okay. Then later they came to know that the electric field and magnetic field are interrelated. That was in 1820. Okay. So when Oersted was doing some experiment related to current electricity. Okay. In 1820, Oersted was demonstrating some experiment which were related to current electricity. Okay. So he was doing some experiment where he took a conductor. Okay. He took a conductor like this. Then he allowed a current to pass through this. So he was explaining something to the other scientist. Then suddenly he observed that when he allowed the current to flow from P to Q in this direction, he observed that the magnetic needle kept close to the conductor. This is the magnetic needle. Okay, it will have its north and south. This magnetic needle got deflected towards one side. So Oersted was surprised with this. Why this magnetic needle is getting deflected? Initially, he thought that probably there may be some magnetic material around. That's why this magnetic needle is responding for that. That's why it is getting deflected. He continued with his experiment. In the same experiment, what he did, he changed the direction of current. Here you can observe it was from P to Q. Then this magnetic needle got deflected towards one side. Then he continued with his experiment. In the next experiment, he changed the direction of current. Now he allowed the current to flow from Q to P. Okay, it was his experiment. Okay, then again he observed that the magnetic needle kept close to that, again got deflected but in the opposite direction. This really surprised him. What is happening here? Then what he did, he left his actual experiment. See, this is how they discover all these things. He left his actual experiment. What he did, he took a conductor like this. Okay, below this conductor, he placed a magnetic needle. Okay, then when he allowed the current to flow through this, then he observed that the magnetic needle got deflected towards one side. Okay, so before that, what he did, he don't wanted any interference of magnetic field, so he removed all the magnetic field nearby. Fine. Then he took a conductor, say PQ. Then below this conductor, he placed this magnetic needle. Then he allowed the current to flow from P to Q. Then he observed that as soon as he allowed the current to flow from P to Q, the magnetic needle got deflected towards one side. Okay. Then he went on increasing the strength of the current. Means first he allowed 1 ampere, then he allowed 2 ampere, then 3 ampere like this. Then he observed that the deflection in the magnetic needle also went on increasing. Then for the first time, Oersted thought that there must be some relation to the flow of whatever this current through the conductor and the deflection of this magnetic needle. Then in the next one, what he did, he allowed the current to flow from Q to P. Then he observed that again this magnetic needle got deflected, but in the opposite direction. Hence, for the first time in 1820, Oersted concluded that, okay, he was the first person to give an idea. Okay, so many scientists worked on this. Whatever the idea of magnetic field we got now, it is because of all this. So for the first time in 1820, Oersted said that whenever we pass the current through a conductor, this conductor carrying current will create its own magnetic field. Hence, for the first time, he told that this electric field and a magnetic field are not separate one. Okay, electric field can create a magnetic field. That is, a conductor carrying current can create a magnetic field. This was the first idea given by Oersted in 1820. Okay, he didn't go in detail. As soon as he gave this one, the scientists started studying about this magnetic field. Okay, so a current carrying conductor can create a magnetic field around itself. That's why Oersted said, hence, when you keep this magnetic needle below this conductor carrying current, it is getting deflected because this conductor carrying current is creating its own magnetic field. Hence, electric field and magnetic field are not separate entities. Both are interrelated. Electric field can create a magnetic field. Then in 1835, some other scientists started thinking in reverse way, because electric field can create a magnetic field means why not reverse is possible. Reverse means why not magnetic field create a electric field? Because in our physics, symmetry is the beauty of physics. This is what Einstein says. Symmetry is the beauty of physics. Means if it is possible in one way, that is a conductor carrying current can create a magnetic field, means reverse also must be possible. That was proved in 1835. See, in 1820, Oersted experimentally showed that a conductor carrying current can create a magnetic field. In 1835, two scientists, Joseph Henry, okay, and Michael Faraday, they proved opposite of this. Okay, opposite means obviously they showed that a change in magnetic field can create an electric field. So it took nearly 15 years for them to prove the reverse, because they know symmetry is the beauty of physics. If it is one way possible, other way also it has to be possible. So in 1835, two scientists, Joseph Henry, Michael Faraday, showed that whenever there is a change in the magnetic field, it will create its own electric field. So hence, from 1820, that is 19th century onwards, scientists started studying both. There were no separate entities as such. Electric field is in turn related to magnetic field, and magnetic field is in turn related to electric field. Okay, so this is what we are going to study in this particular chapter. Clear? Okay, let us observe the experiment done by Orested. Okay, so see, here is the diagram. Here he took a conductor. You can see below that he is placing a magnetic needle. Then he allowed the current to flow. When there was no current, observe the first diagram. When current is zero, the magnetic needle was pointing just from north to south, because I told you in previous chapter, Earth has got its own magnetic field. Hence, whenever you suspend a magnet, always it should come to rest along north and south. So it was simply pointing north and south. Observe second diagram. You can see you are allowing the current to flow in one direction. Then immediately you can observe the north pole of the magnetic needle got deflected towards left side, as shown with a red color. Then he changed the direction of current in the third diagram. Okay, you can see again the magnetic needle got deflected. Observe the red point, it got deflected towards the right. Hence, for the first time, Oersted concluded that this conductor carrying current must be creating its own magnetic field. That's why the needle, depending on the direction of current, either it will get deflected towards the left or it gets deflected towards the right. So this tells you that if the magnetic needle is getting deflected on either side, the magnetic field must be a vector quantity. Clear? Magnetic field must be a vector quantity. That's why whenever you pass the current in one direction, the magnetic needle get deflected towards one side. Again, when you change the direction of current, magnetic needle gets deflected in the opposite direction. So this concludes that what is the direction of magnetic field created, it depends on the direction of current. Hence, magnetic field must be a vector quantity. As soon as he gave this idea, the scientists started working on this. Okay, some wanted to find out why the magnetic needle is getting deflected like this. How do I find out the direction? Then some other scientists started working. How do I calculate how much magnetic field it creates? Because in his experiment, Oersted observed that, I told you, as he increased the strength of the current, he observed that the deflection in the magnetic needle also went on increasing. Then obviously it indicates it has something to take with the amount of current. Okay, so other scientists started working out how much magnetic field is created by this, whatever the conductor carrying current. So whatever the idea I got now, it is because of all this. So this is what we are studying in this particular chapter. Clear? Anything with respect to Oersted experiment? 2 minutes. Any clarification? No doubts? Okay. So remember, magnetic field, time being, you can assume, we will see the exact definition later, is the space or a region around the current carrying conductor where its influence can be felt. Means where you can feel the presence of the magnetic field. Fine. So as soon as he gave this, first they started thinking about the direction. The direction of the magnetic field was first given by amperes. Okay. See, first, rather than defining what is magnetic field, first they started thinking about direction, because they know if it is a vector quantity rather than magnitude, it is very important to talk about direction. So the first idea was given by amperes, and it is called Ampere's swimming rule. Okay, see, there are different ways by which I can find out what is the direction of magnetic field created by a conductor carrying current. Fine. One method is this. Okay, so try to remember, they may ask for 1 mark, but I will tell you which method is easy for you, which you can remember. So according to this Ampere's swimming rule, if a swimmer is imagined to swim, okay, along the conductor in the direction of current, facing the needle, then observe the north pole of the needle will deflect towards his left arm. This is one way how we can find out. For example, suppose if I consider this is the conductor. Imagine a swimmer is swimming in the direction of current, okay, facing the needle. Then obviously what will happen? The north pole of the magnet, okay, magnetic needle will deflect towards his left. This is one way how we can find out. For example, if you observe in the diagram also, when the current is upwards, you can see the red point of the magnetic needle is deflecting towards the left side. Similarly, if you change the direction of current here, then obviously it will come towards his right. Okay. So if they ask statement, what I am supposed to write? If a swimmer is imagined to swim along the conductor in the direction of current, then the north pole of the magnetic needle will get deflected towards his left. Okay. So how do I remember in terms of mnemonic? If a current flows from south to north, here you can observe it is flowing from south to north. And the wire is held over the needle. This wire is kept above the magnetic needle. The north pole of the needle is deflected towards the west. So you can remember this one in terms of snow. Okay. If current is from south to north, okay, and the magnetic needle is above, over the conductor, then the magnetic needle will get deflected towards the west. If it is from north to south, okay, NSOE it will become, then it will deflect towards the east. Clear? This is one way, but many people couldn't follow this. Okay. Then one more scientist gave, okay, Cork, he gave one more rule. It is called screw rule. Okay. Imagine if I take a screw like this. This is the head of the screw. Okay, this is the head of the screw, and this is the tail of the or tip of the screw. So according to him, consider a right-handed cork screw. Okay, means you have to hold it in right hand, not left hand. This is very important. Okay, and if you rotate this one, for example, if I rotate the head in anti-clockwise like this, observe the tip is going to advance in the forward direction. Imagine as if you got a screw, you rotate in anti-clockwise. Okay, when you rotate in anti-clockwise, the tip of this will go in the upward direction. So I'm rotating anti-clockwise. Okay, so in whichever direction the head rotates, it gives the magnetic field direction. Then in whichever direction the tip is moving will give you the direction of current. Check both are same. Here you can see current is upwards. Here also tip is moving upwards. Here the magnetic needle got deflected towards the left. Here you can see it is rotating anti-clockwise direction. Okay. If you make it clockwise, then obviously the tip will come down. So I told you if the current is downwards, then the magnetic needle will deflect towards the right. So this is called right-handed cork screw rule, according to which when I rotate a screw in whichever direction the head of the screw rotates, if it gives the direction of magnetic field, then in whichever direction the tip of the screw moves will give the or advances will give the direction of current. Okay, so this is another way, but still this was a confusion. Therefore, finally we use what is called a right hand clasp rule, or maybe in school you studied this as thumb rule. Those who are ICSE people might be knowing this. Okay, but use either you call it as right hand clasp rule or call it as thumb rule. Okay, all of you have to do this. Take your pen, hold it in your right hand. Do it, then only you will understand. Suppose if this is your pen, hold it in right hand, not left hand. In exam, this is the mistake what generally you do. Keep in mind, in this chapter, direction is very, very important if you want to solve numericals, if you want to solve derivation and all. So hold the pen in right hand such that observe my thumb and my fingers. So whenever I clasp this, assume this pen as a conductor now. If I clasp this one in my right hand, okay, such that the thumb indicates the direction of current, then the remaining finger should indicate the direction of magnetic field. Okay, I repeat, whenever I take a conductor carrying current, if I clasp it, clasping means holding it. If I hold it in right hand, such that the thumb indicates the direction of current, then the remaining finger should indicate the direction of magnetic field. So you compare with the screw. I told you when you rotate the head of the screw in anti-clockwise, you can see my fingers are pointing anti-clockwise. Okay, and the thumb is pointing upwards. So I told there also in screw rule, the tip of the screw will move upwards. Here also, if the current is upwards, then remaining, remember, the magnetic field will be anti-clockwise. Suppose if the current is downwards, see what is happening to my fingers. It becomes right hand. Sorry, clockwise. Clear? So hence, easy way to remember the direction of magnetic field. But important is, if the conductor is a straight conductor like this, it is applicable only for straight conductor. Remember, in this chapter, we are going to study two conductors. One is straight conductor, another is the circular conductor. We will see when circular conductors what to do. Time being, I'm talking about straight conductor. So if I take a straight conductor, if I clasp it in my right hand such that the thumb points the direction of current, then the remaining finger should point the direction of magnetic field. Hence, whenever I take a conductor, if this carries current, remember it is surrounded by magnetic field in the form of concentric circle. And current is possible either upwards or downwards. If the current is upwards, magnetic field will be anti-clockwise. If the current is downwards, then the magnetic field will be clockwise in direction. Clear? I'll give 2 minutes, check this. Still any doubts, I'll clear it fast. Here diagrams are there, you can cross check. If you don't know how to find the direction, again I'm telling you, this chapter will become impossible for you people. Okay, even if you miss one single class, you cannot follow anything. It is up to you. Fast. Any doubts? Are you following or not?
Yes, sir.
Out of 55 students, I get answer from one single student. Okay, anyhow, it is up to you people. Check any clarification. Obviously, next class, I will ask all these things. I'll ask what is Ampere swimming rule, what is right-handed corkscrew rule, what is right-handed clasp rule, and all that. Okay, so from this we understood that whenever I take a conductor carrying current, it must create its own magnetic field. Fine. Then how do I represent a magnetic field? Observe this diagram, very, very important. If it is a uniform magnetic field, remember I told everything what is meant by magnetic field and all in the previous chapter. If it is a uniform field on the plane of the diagram, so plane of the screen, we represent them by equidistance line parallel to each other. All of them are pointing in the same direction. Observe the arrow here. Okay. So a uniform magnetic field is represented by a straight line, a parallel lines, which are equidistant from one another, and all of them are pointing towards same direction. Suppose if I take a uniform field perpendicular and into the plane of the diagram, assume your screen itself as a page, okay? Then if the magnetic field is perpendicular, now assume whatever the pen I'm holding, it is perpendicular to your screen. Then obviously, if it is a uniform field, perpendicular and into the plane of the diagram, means magnetic field is going into the screen. Or you can say away. I am the observer now. I'm away from the observer. Is always represented by a cross here. Remember, okay? Cross and observe the separation. They are all equal. So if you represent a cross, then you are indicating magnetic field is perpendicular to the plane of screen, page, whatever you consider, and it is into the plane of the paper. Okay, it is going into the plane of the paper, magnetic field. By chance, if I represent that by dot in as shown in third diagram, then again here magnetic field is perpendicular to the screen, but it is away from the screen or towards the observer. You remember the way you want, whether you want to talk in terms of observer or you want to talk about plane of paper, because this is how they will mention in the exam when they give numericals, even your CET, NEET exam, whatever. So remember, if they show cross, then understood the magnetic field is perpendicular to that page. It depends, either it is away from observer or towards the observer. If it is a cross, it is always away from the observer. If it is a dot, then it is towards the observer. Clear? This is how we represent a magnetic field. Clear? 2 minutes. Any doubts? Fast. Hope all of you are in front of your mobile or in front of your desktop or in front of your laptop. Last class only I've seen some people were not at all there. Anyhow, it is up to you. Anything? Fine. So now I know that if I take a conductor carrying current, it creates its own magnetic field. Now the question is, how do I find out how much magnetic field is created? Or I want to know what is the definition of this magnetic field. Because after the discovery by Oersted, there is no need to study separately the magnetic field and the electric field. Both are interrelated. Now the definition of magnetic field, a space around a magnet where another magnet experiences force, is ruled out. I cannot use it anymore. Then how do I define it? For that, first they found out, important from exam point of view, what is the force. See what exactly I'm writing. Force acting on a charged particle moving in a uniform magnetic field. So this clearly tells you that whenever I take a charged particle, if this charged particle moves in a uniform magnetic field, it is going to experience a force. So only a moving charge, that's why the name of the chapter, moving charges and magnetism. Moving in a uniform magnetic field, that also charged particle. This clearly indicates that if I'm talking about a neutron, if you allow a neutron to move in a magnetic field, it won't experience any force because it is uncharged. Okay, so I want to know what is the force acting on a charged particle moving in a uniform magnetic field. For 3 marks, they've asked obtain an expression for force acting on a charged particle moving in a magnetic field. Or sometimes they've asked derive F is equal to B Q V sin theta. Okay, where F is the force B is the magnetic field. I told in the last chapter. Magnetic field is denoted by letter B. And you know Q is the charge of a charged particle. V is the velocity with which it is moving. And theta is the angle made by charged particle with the magnetic field. Okay, let us see how to derive this. Important one for 3 marks from exam point of view. For this, what I will do, first let us consider a magnetic field acting in this direction. Okay, it can be in any direction, not necessary that it has to act like this. So magnetic field is in this direction. Let us say along x-axis. Then let us say a charged particle moves in this magnetic field, which makes an angle theta. Okay, with the magnetic field. Observe, I'm taking V is the velocity with which a charged particle is moving in a uniform magnetic field B, that is represented here. Let theta be the angle. This is all what you should write in the exam. Theta is the angle made by the velocity of the charged particle with the magnetic field. Now you can see velocity is a vector, magnetic field is also vector. Hence, we resolve this velocity into two quantities, into two vectors. Because whenever two vectors are acting at some angle, remember, it must be resolved into two components. Because two vectors are at some angle. Let us say this is the vector along the magnetic field. Fine. I'll take one more vector which is perpendicular to it. Okay, so I resolved into two component. Hope the diagram is clear. Check again, anything you want to ask. Fine. Now if I take the component along the magnetic field, remember wherever you show the angle, that is always cos component. So this is V cos theta. And wherever you show perpendicular component, perpendicular to this theta, that is always sine component. So this is V sin theta. Clear? So I'm going to join this. This is according to resolution of vector, what you studied in first PSC. So horizontal component is given by V cos theta. Vertical component is given by V sin theta. Now, if I say if F is the force acting on the charged particle Q, charged particle Q, experimentally it is found that F is proportional to Q. Okay, so they observed that whatever the force experienced by this charged particle depends on magnitude of charge. Okay, so if I take magnitude of electron and proton, you know both are same. Hence I can say both will experience same amount of force in the same magnetic field, provided they move with the same angle and with same velocity. Clear? See, don't write just equation. You have to write in terms of words. The force experienced by a charged particle is found to depend on magnitude of charge. That is, as the magnitude increases, force also increases. Clear? Second one, if I take, it is found that whatever this force acting on the charged particle is proportional to V sin theta. Means it depends on velocity, but velocity has been resolved into two components. So it depends on sine component, not on cos. Again, is experimentally seen. Because when they allowed the charged particle to move along the magnetic field, they observed that theta was 0, sine 0 is 0, force was also 0. Hence, they took the sine component, not the cos component. Hence, second factor, it is found that the force acting on the charged particle is proportional to the component of velocity, that is sine component, that is v sine theta. Then third one, they found that whatever this force acting also depends on the magnitude of the magnetic field, that is B. F is proportional to B. More is the magnetic field, more will be the force experienced by the charge particle. Clear? Check all the 3 points again. You have to write everything in words. Okay. Now, if I combine all this, I can write F is proportional to BQV sin theta. Okay. Or this implies, whenever we remove the proportional, we will put some proportionality constant K into B, Q, V sin theta. And if I take the SI system of unit for a given magnetic field for a given angle, it is found that the value of proportionality constant K is 1. Therefore, I can write the force experienced by a charged particle moving in a magnetic field is given by BQV sin theta. Clear? This is the expression for force acting on a charged particle moving in a uniform magnetic field. Clear? I'll give 2 minutes. Check this. Any clarification, I'll clear it. Fast. So using this equation, we can define what is meant by magnetic field. So check the derivation, how the velocity has been resolved into 2 components. I told you 2 vectors are acting at some angle. To find out what is the resultant, I'm resolving velocity vector into 2 components. One along the horizontal given by v cos theta, one along the vertical given by v sin theta. Keep in mind, wherever you show the angle, that component is always cos. And experimentally, they found that F is proportional to Q, F is proportional to V sin theta, F is proportional to B. Clear? Fine. So, if I take, I know what is the magnitude of force. It is given by BQV sin theta. Now, I want to know when it will experience maximum force and minimum. 2 marks question, important. Obviously, force on the charged particle is maximum when theta is 90. That is, the charged particle should move perpendicular to the magnetic field, because sin 90 is 1. Correct? Therefore, what happens? The force will be maximum. And remember, maximum force is given by B, Q, V. For a given magnetic field, for a given charge, for a given velocity, force depends only on angle. When it will experience maximum force? When theta is 90. Theta 90 means what I'm supposed to write? When the charged particle moves perpendicular to the magnetic field. This way, remember, I'm not taking cos component. Because if I take cos component, if it moves perpendicular, theta 90, cos 90 is 0. It should not experience any force at all. But experimentally, what you are observing, it is experiencing maximum force. Therefore, we are going for sine component, not cos. Then second one, when it will experience minimum force. Remember, minimum means obviously 0. Obviously, minimum when theta is 0, because all of you know sin 0 is 0. Therefore, the minimum force experienced is given by 0. Remember, whenever a charged particle moves parallel to or anti-parallel, okay? Even if I take theta 180, sin 180 is 0 again. Remember, therefore, I can say whenever a charged particle moves parallel or anti-parallel to the magnetic field, again it is going to experience minimum force or zero force. They've asked for 2 marks number of times. Either they will ask you derivation for 3 marks, or they've asked when the charge particle will experience maximum and minimum force. Remember, don't simply write theta 90. You have to write in words that a charge particle, when it moves perpendicular to the magnetic field, it is going to experience maximum force. Whereas when it moves parallel or anti-parallel, parallel means theta 0, anti-parallel means theta 180. In both the cases, sine 0 or sine 180 is 0, therefore force is also minimum. But you know force is a vector quantity. Then how do I express this in terms of vector form? Even 1 mark question. They have asked for 1 mark, express the force acting on a charged particle in a vector form. Okay, so remember, if I take vector form, F vector equals, it is V cross B, not B cross V. Okay, because it is a cross product. You know, if I take V cross B, F will become perpendicular to V and B. If you take B cross V, then F will go down. Okay, so it depends. That's why remember, very, very important, when you write in vector form, okay, it should be V cross B, and you know charge is a scalar quantity into Q. Okay, or you can write it as Q into V cross B also, either way. But important is you cannot interchange V and B, because direction of F depends on V and B. This clearly indicates that F must be perpendicular to the plane of V cross B. Okay, F must be perpendicular to the plane lying velocity and vector quantity B. Clear? So this is all about the force acting on a charged particle placed in, moving in a uniform magnetic field. I'll give 2 minutes, go through all this. Check. See any clarification? Check how you write in vector form when it will experience maximum minimum force and all. Okay. Now same thing you can check here also. Here I have not shown the resolution, okay, but understood. See how when it lies. Important is Q is positive upwards. If the same charge is negative, the direction becomes downwards. Okay. But observe B and V are perpendicular. F is perpendicular to the plane containing them. Okay. Check this. Clear? I've written in vector form also. It is always V cross B. Another thing you have to observe here, note, if a charge particle is at rest, see, only a moving charge can experience force. Because when I told a conductor carrying current means what? Charges are flowing inside that conductor. Correct? Same way here also. If it is at rest, it will not experience any force. And if charge particle moves parallel or anti-parallel, just only I told F is 0. If charge particle moves perpendicular, for a neutral particle, I told you for neutron, since no charge, it will not experience any force. But remember, for negative charge, the direction force becomes opposite to positive. Here, whatever direction I am talking, remember, we assume positive charge. I told you because earlier scientists thought only everything is because of positive charge. But later, after discovery of electron, they came to know that it is not due to the negative positive charge, but it is due to electrons which are negatively charged. Clear? So in the next class, we'll see how to find the direction of this force. That is, we are going to use Fleming-Lefland rule. See, already we have seen how to find direction of magnetic field. Okay. So I'm going to come across number of directions. You have to remember properly. Try to understand. Fine. So we'll check in the next class. Okay, we'll continue in next class. Fine.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.